Welcome back to our discussion on membrane structure and function, and we're going to start looking at transport today. So previously we've discussed selective permeability and what structural features of the membrane cause it to be structurally selectively permeable. And so far we talked about the hydrophobic core and its contribution to selective permeability, and we're going to introduce some new structures and new properties of the membrane which contribute to selective permeability. So let's get started. But before we get into this issue of structure, function, and selective permeability and movement of substances across the membrane, I want to direct you to a feature in your textbook. All throughout your textbook, there are these little boxed features which are titled biology principles. And so I put one up on a slide here. And this is here is a biology principle, which is structure determines function. So I'd encourage you to look for these principles all the way through your book. And we've touched on another one. Homeostatic regulation is another important biological principle. And people always ask me, how do I know the stuff that I know? And part of the answer to that question is how I organize the material in my brain. And there's no difference between your brain and my brain, just how we organize information and then access information. So my understanding of biology is arranged around a number of principles, probably 5 to 7 general principles, I would say. And this is one of them: structure determines function. So look for these principles every time we talk about a piece of content. And the membrane structure function one is a classic example of how you can use a biological principle to help your understanding. So that being said, let's move on to look at some mechanisms by which solutes can move across membranes. Now don't forget, a solute is a substance dissolved in a solvent where the solvent is doing the dissolving. So glucose would be a solute in water. Sodium chloride would be a solute in water, and water would be the solvent. So some molecules, some substances can move across the membrane by simple diffusion. This is a form of passive transport. It requires no external input of energy. This is a random process, and this is one of the big misconceptions about diffusion. Diffusion is random, and it is due to the kinetic energy that you find in all molecules that exist above absolute zero. So all molecules are vibrating, and they've got rotational and lateral motion due to the amount of heat in a system, and that gives them some kinetic energy. And so they're all moving. That means they're bouncing into one another and to whatever they are enclosed within, and that creates movement, random movement. So molecules will simply diffuse along random paths called random walks from one place to another, and you can't necessarily predict that pattern of diffusion. And so things will diffuse across a biological membrane if they have certain characteristics that we've talked about, if they're small and if they're non-polar, or if they're small and have some polarity, like a water molecule is so small that it will diffuse across a membrane. So when does simple diffusion occur across a membrane? Well, always. It is always occurring because diffusion is a random process. So even if you've got two equal concentrations separated by a membrane, you will still have diffusion back and forth because this is a random process due to the amount of heat in a system. Now, if we put a high concentration of a diffusible solute on one side of a membrane and a low concentration on the other side, now we will have a net movement from one side to the other until we get equilibrium, but this is still a random process. So that is simple diffusion, movement across a biological membrane without the aid of a protein, without the input of energy. Now, we can make this a little bit more complicated. Here's another form of diffusion. This is still the random movement of molecules, except these are molecules that need some help to move down, to move across the membrane. So things like glucose, anything which is larger than say a water molecule or indole or glycerol, something like that. Larger molecules, more polar molecules, and charged molecules and ions. So this is how most ions will move across a membrane. This is facilitated diffusion. It's called facilitated because the diffusion process is helped or facilitated by a protein. This type of protein we're looking at here is called a channel. And so channels are either closed or they're open. And so there are mechanisms in the cell which can either close the channel or open it. And so they're constantly in this state of either being open or closed, and they can flip backwards and forwards, and that can be regulated. And so if we have high concentration on one side of a membrane, low concentration on the other side, and we're dealing with like sodium or chlorine or calcium, you can't just have that ion moving across the membrane by simple diffusion. You have to have a protein. And so if the protein, like this channel, opens, then we will have diffusion in a net direction down the gradient from high concentration to low concentrations via facilitated diffusion. So that's a second general mechanism. We'll expand on these in a later section. Then the last mechanism we can look at to move things across membranes is called active transport. So active transport again uses a pump, but it is going to work against a concentration gradient. So a concentration gradient, if you don't understand what a concentration gradient is yet, is where you have a high concentration on one side of the membrane and a low concentration on the other side of the membrane. There's now a gradient here, and the gradient is downhill in that direction and uphill in that direction. So diffusion, it works in both directions, but if we want a net movement of diffusion, that will only work down the gradient. It's like balls roll downhill, they don't randomly roll uphill. So diffusion will happen in a net direction without an input of energy. But if we've got to move something up the gradient, that's like pushing a ball up the hill, and so we've got to do some work there. So this is called active transport. This is when we move a solute from a low concentration to a high concentration across a biological membrane. And as what you're looking at here is a pump. And so these pump molecules, they're proteins in the membrane. So go back to thinking about, how did this protein get here? Well, it would have started to be translated in the cytoplasm. Then the ribosome would have gone to the rough ER. And then the protein would have been translated so that it gets inserted into the membrane of the rough ER. And then a little vesicle would take that membrane, including the protein, to the Golgi, and then it would go to the membrane. And when the vesicle fuses with the membrane, that's how this protein gets there. So this pump is using the energy that's contained in ATP. And so when we break the ATP down, or when the pump breaks the ATP down, that releases the energy to move a solute from a low region of concentration or a low concentration area to a high concentration area. And we're going to look at these in a lot more detail. There's one of these pumps in your neurons and in many other cell types as well, which uses about 1/3 of the ATP you produce each day. Now you produce about 9 kilos. So for, let's say, a man of average body mass, let's say that's 90 kilos, that is 10% of their body weight every day, making and breaking down ATP. And 1/3 of that, 3 kilos, 3 kilograms of ATP goes to driving this one type of pump that you need to make your cells work, and it's super important in neurons. So that's active transport. That's going to move a solute up a gradient. Okay, so what I'd like you to do is sketch this table down and then look at the list of molecules at the bottom. I've got a list of molecules from A through M. And then I want you to categorize whether these can move freely across a membrane or if they need to be helped. Now, I want you to assume here that there's a concentration gradient. So if you're thinking about carbon dioxide, think about it as though it's your blood, for example, entering the tissues in your lungs. So think about that situation. You've got a high carbon dioxide concentration in the blood that enters the lungs and a low concentration, relatively speaking, in the air spaces in your lungs. And so there's a concentration of carbon dioxide across the membrane. In that case, will the carbon dioxide move freely across the membrane from inside the cells to inside your lung, or must it be helped? Okay, so think about it like that. Assume there's always a gradient of these things. So work through the list. If there are any here you don't know what they are, then go and look them up and look at their chemical properties. So you've got to go back to looking at the size, are they charged, what kind of covalent bonds do they have. So give that a go, and pause the video, give that a go, and if you've got any problems with that, put your table in a discussion in Canvas and let's have a conversation about it there. Okay, let's just have a quick check. Let's see how you get on with this question, and then I think we'll wrap it up in this section. So how'd you get on with this question? And you can assume that there's a concentration gradient here. So okay, so that's it for this short video. What we've talked about here are three general mechanisms for moving solutes across a membrane: simple diffusion, facilitated diffusion, active transport. Key here is you're being able to look at a molecule, so you're given the structure of a molecule, and determine then how would that move across a membrane if you're given some information about concentration gradient and the like. So that's it for now. I will see you soon.